Hello, my name is Nathan Rooke. I am a part of the buckling group with Corey Smith, Ross Benz, and Jeff Lau. This is an overview of the presentation for your reference. We'll begin with an introduction to buckling and some examples, followed by finite element methods for various types of buckling, but primarily column buckling, and finally, we'll talk about our ANSYS simulation and its results. So what is buckling? In engineering, buckling is the sudden change in shape of a structural component under load, such as the bowing of a column under compression. If the structure is subjugated to a gradual increasing load, when the load reaches a critical level, a member may suddenly change shape and the structure and component is said to have buckled. Buckling may occur even though the stresses that develop in the structure are well below those needed to cause failure in the material of which the structure is composed. Further loading may cause significant and somewhat unpredictable deformations, possibly even leading to complete loss of the member's load-carrying capacity. However, if the deformations that occur after buckling do not cause the complete collapse of that member, the member will continue to support the load that caused it to buckle. If the buckled member is a part of a larger assemblage of components, such as a building or a bridge, any load applied to the buckled part of the structure beyond which caused the member to buckle will be redistributed within the structure. As an example, some aircraft are designed for thin skin panels to continue carrying load even in a buckled state. Moving on to a simple buckling example, if the load on a column is applied through the center of gravity or centroid of its cross-section, it is called an axial load. Load at any other point in the cross-section is known as an eccentric load. A short column under the action of an axial load will fail by direct compression before it buckles, but a long column loaded in the same manner will fail by springing suddenly outward laterally in a bending mode, which is buckling. The buckling mode of deflection is considered a failure mode, and it generally occurs before the axial compression stresses can cause failure of the material by yielding or fracture of that compression member. The figure on the left shows a long, slender column under compression in a hydraulic press. The left part of that image shows before buckling, and the right side of that image shows after buckling. This column is considered to be buckled when a point on the cross-section of the column has laterally translated beyond the footprint of the column's base. So before buckling, it's a straight line, or basically a straight line, but after buckling, it forms somewhat of a curve, or in this case, a triangle. The diagram on the right denotes this translation with the variable y. Here's an interesting example of buckling in soda cans. Have you ever seen the party trick where a fully grown person can balance on an emptied soda can? Even though the can's wall is only 0.1 millimeter thick aluminum, it can sustain the load as long as its shape is perfectly cylindrical. The axial stress is below the yield stress, which is easily checked by dividing the force by the cross-sectional area. However, if you press lightly against a point on the cylindrical surface, the can will buckle and collapse. The load needed for the can to buckle the perfect cylinder, or in this case, the soda can, is higher than the weight of the person performing the trick, while only a slight distortion will significantly decrease the load bearing the capacity. This fun engineering trick was researched by a team at Harvard. The team clamped an undented empty Coke can between two metal plates to produce a force along its vertical axis. They then poked the side of the can using a metal ball attached to the end of the rod, continuously pushing the ball further into the can until it buckled with a loud snap. Repeating this measurement with various axial force strengths and ball sizes, the team mapped the conditions needed for buckling to occur. This map defines the can's, quote, stability landscape, unquote, whose features indicate which combinations of parameters result in a crushed can and which don't. For example, a can never buckles if the axial load is below a certain value, regardless of how big the dent is. But beyond a threshold axial load, all cans buckle once the dent is sufficiently deep. Because this sudden offset effect is indicative of a general behavior known as a nonlinear instability, the team suggests that all dented can-shaped objects have a similar stability landscape. If this universality holds, then other researchers might be able to use the stability maps for this Coke can to predict the strength of a space rocket or another similar object just by gauging its response to a gentle poke from the side.
A column is a long structure of beams that carry axial load. Failure occurs when the load reaches a critical level. A column can categorize into three different types, and each type of column has a different failure mode. The type of a column is determined by its slenderness ratio. The slenderness ratio is the length of the column divided by the radius of gyration of the column. A long column has a slenderness ratio between 120 to 200. Its failure mode is buckling. An intermediate column has a slenderness ratio between 40 to 120. Its failure mode is a combination of buckling and crushing. And a short column has a slenderness ratio of less than 40. And its failure mode is crushing. To calculate the critical load of a column, we can use the Euler's column formula as shown on the screen here. And one thing we would like to point out is the value of K. K depends on the end condition of the column. And there are 4 cases. If a column has one free end and one fixed end, K is equals to 2. For both pinned end, K is equals to 1, and this is also called an ideal case. One free end and one pinned end, K is equals to 0.7, and both fixed end, K is equals to 0.5.
So to continue our introduction to column buckling, we're going to go over a couple of other types of buckling, as well as some complications that can make calculations of buckling a little more difficult, but make them more realistic. So one of the other types of column buckling that is generally overlooked when we do our traditional buckling calculations is torsional buckling. And there's a good YouTube video linked. But this can occur generally with open cross-sectional shapes like L and C and I-beams, especially if the shape is non-symmetric, like this weird C-beam I made down on the bottom right, where the bottom horizontal is much longer than the top horizontal. And what that does is it creates a major difference in the second momentary of inertia in the various axes as well as locally. So like the bottom of the lower horizontal in that image has a very different stiffness from the top horizontal in that image. And this is a top-down cross-sectional view of a theoretical beam. And we get this mode of buckling that's torsional instead of the usual flexural mode of failure. And we can see that kind of on the left image where we have the 2 possible constituent directions for flexural buckling, and then we have the third image, which is this torsion buckling. And as with flexural buckling, if you have a high enough slenderness ratio and the loads are low enough, you can get elastic buckling. But if the loads are high and things are short, chubby, you get plastic buckling. And then torsional flexural buckling is kind of a combination of torsional buckling and flexural buckling, but they're happening at the same time. And actually, I think you'd be hard-pressed to see torsional buckling happening by itself. You would normally see the two happening together. And the reason torsional buckling occurs, as I alluded to, is this big difference in area moment of inertia. But what happens is the center of shear stress kind of shifts away from the center of cross-sectional area, and this can cause the whole structure to twist along its length as you compress it. Continuing on, we also have plate and local buckling, which they're 2 sort of separate things, but I've combined them because they can be similar. And plate buckling is similar to our regular old Euler buckling of columns, but with thin plates, they can still carry quote-unquote useful loads when they're buckled. So you might visually see, like in this bottom left image, you can visually see that this plate here is buckled, but it's still capable of carrying a useful load. It doesn't just immediately collapse. And plate buckling, it isn't just necessarily a thin piece of sheet. It can also be a shape made from plates, like an I-beam. and we can see this plate buckling occurring in shapes that are made from plates like the L beam that's in this bottom left picture, especially when the ends are fixed. And for plate buckling, unlike for the traditional column buckling we're used to seeing, we need to take into account potential higher orders. So normally, and this is the middle image, normally we only look at the first mode of buckling when we do our calculations, whereas we go from a straight line to this kind of bowed shape on the top. But for plate buckling, depending on the width to thickness and length ratios of the plate, you can get these higher orders that we see on the right picture, where we see these red high spots and blue low spots, and they form kind of a sinusoidal-ish wave, which needs to be taken into account. We can't just use the first order buckling equation. And plate buckling can also, with these higher orders, help explain why some types of local buckling occur. So if we look at this right image, let's take any given red spot, right? That's a high local buckling point. If that red spot happened to have an imperfection in it, we could see local plastic buckling, which could cause failure of the whole structure. And then lastly, something that tends to be overlooked is warping. And this is difficult to explain, and the YouTube video does a very good job. But if we imagine an I-beam of a given length, and we have two planes sitting on the ends, each one on each end of the I-beam. If we bend the I-beam, like if we put a compressive load on it and it starts to buckle and it bends and bows, those two planes would no longer be parallel to each other, right? They would be large planes, like infinitely long planes. They would now intersect somewhere. But anyway, they're not parallel to each other anymore. But if we had fixed ends, those planes would have to be parallel to each other because the ends are fixed. And what that would do is those planes wanting to move out of being parallel and them being forced to stay parallel would add additional stiffness to the beam that is not necessarily taken into account in our traditional modeling of beam buckling and stiffness. And we see the highest stiffness increases in asymmetric open shapes, like the shapes that we saw in slide 7 that were subject to torsional buckling. They see increases in buckling stiffness both due to having this warping effect increasing their stiffness, and if you fix the end, then they have a harder time torquing as well. So on this slide, as a free bonus, to show you kind of a practical example of plate/local buckling, we can see a Coke can that's full being compressed, and the slenderness ratio really isn't high enough for traditional buckling, but what's cool is we can still get plate buckling because it's basically a round, thin plate. So we'll actually see some rings, some radial expansions happen as this gets compressed. And it can't do a full sinusoidal sweep because it can't expand inwards because the liquid's incompressible. But you can see these rings form along the outside, and we'll get to 6 rings, which would be, if we assume that the non-compress inwards ability, you would get, what would that be, 11th mode, right? So that's definitely a higher order compression, higher order buckling failure that we wouldn't normally take into account that needs to be taken into account in this case, which is very difficult to model, but it looks really cool when you crush Coke can.
Here's a simple example. So we have a 58 inches long stainless steel tube with 1 inch outer diameter and 0.92 inch inner diameter. One end of the tube is fixed and the other end is free. And K is equal to 2 in this case. The module of elasticity is 29 million psi. The moment of inertia of the tube is 0.02746 inches to the power of 4. Using the Euler's buckling formula, we can find out that The critical load for this particular tube is equals to 584 pounds.
My name is Corey. I'm going to start with the ANSYS portion of our project, covering buckling. And I'm going to start by opening up Workbench. And this is going to be our desktop, or literally like our workbench, where we're going to grab all of our modules or tools that we're going to use from our toolbox right here. And these are things that we're going to use to build up our system in order to solve our problem that we're trying to face. So each of these different tools in our toolbox, these are like modules, they can each do FEA using its own set of equations, trying to simulate different results. Going through our toolbox, we have eigenvalue buckling, which we'll be using for this project, electric, dynamics, we have many for fluid flow, harmonics for acoustics, hydrodynamics, internal combustion engines, modal analysis and modal acoustics, random vibration and response spectrum, rigid dynamics, static structural, which we will also be using for our project, steady state thermal, thermal electric, topology optimization, transient structural, transient thermal, and turbomachinery fluid flow. So let's go ahead and start off. We're going to grab our static structural and drag it into our project schematic. This created a standalone system, and in this system, for static structural, there are 6 items that we need for our static structural module in order to solve and get results. We need engineering data. This is things like what your material's properties are, those engineering values. These values are often from Material Web or MatWeb, if you're familiar with that. We also have a geometry section, and this is for our model, our part. This could be from SpaceClaim, which is ANSYS's version of SolidWorks, or you can model directly in SolidWorks and export as a step file. A step file, or an STP file, is a file that's used for the standard exchange of product data. So this is a way that you can take CAD from multiple platforms, standardize it so that you can read it in all sorts of different applications, because you can't open a solid part with an ANSYS. It needs to be standardized in order to open. Your model and your setup sections are kind of combined. The model is where you define your mesh and how fine of a mesh you want, or if you want to have an advanced mesh where you want to look at certain points in more detail. The setup section of that in particular is for things like boundary conditions or your applied forces. Your solution and your results sections are for if you're trying to pick certain points and calculate the deformation at a certain location, or how you want your data displayed. These two kind of go hand in hand in solution and results. We need another module to go ahead and add in order to get our completed picture for buckling. And that second module is eigenvalue buckling. And so these are standalone systems. If I were to drag eigenvalue buckling over the top of static structural, it can share that data between the two modules. So if I want to share the engineering data, so what the material is made out of, the geometry, the part that's in SolidWorks, and the model or the mesh, so that I don't have to create this multiple times, I can go ahead and drag and drop it over model, and you'll see it'll create a link in between these two modules so that I can share that information. We also want to output. We also have one more piece of data that we want to share between these two systems. We want to share our solution, which is our displacement at certain points, and we want to share that into the setup category of the eigenvalue buckling so that we can use that displacement in order to find the points of buckling. So we're going to go ahead and drag and drop, and you'll see it's created that link right there. Okay, so now we're ready to start going down and making sure that we have the required information to get to our results. We're going to start with our engineering data. I'm going to go ahead and right click and select edit. So now we're in our engineering data page, and if you've come here before, I oftentimes am struggling to find certain things because I'll accidentally close them. So I'm going to start out by making sure that we have all of our windows visible so that we're all in the same place. I'm going to go ahead and click Reset Workspace. So now we have all of the windows opened up. So in case you were trying to find something and couldn't find it, now it should be there. You'll see as a default, it's selected structural steel as a material that's available for us. In order to find other materials, we're going to go into our engineering data library. And now we have different categories of different materials that are already built into ANSYS. If we needed a custom material, we can then create our own. You can create a favorites list of materials that you frequently use, such as air, steel, aluminum, or any other material that you frequently use. To find structural steel and other similar materials, you can go under General Materials. And down here, we can see some of the general materials, aluminum alloys. Note that this isn't a very specific type of aluminum like 6061 T6. You'll have to then look up the values for 6061 and type them in and edit it so that it reflects the proper material. Towards the bottom of the list, we have other materials like titanium alloy, structural steel, stainless, polyethylene, FR4, and you'll notice that it's very general. It's not super specific. So with all of these materials, you might need to do slight tweaks to make them correct for your application. I'm going to go ahead and add a second material that we can switch to in case we want to use it, stainless steel, and add that into our library of materials that we're actively using. I'm going to go ahead and click the plus sign, and you'll see the little book appear. So now we know that it's available for us to use in our system. Okay, I can go ahead and close this and go back out. Engineering data has a check mark because we have some materials. Now we need to import geometry, and before we import geometry, we need to create our model of what we're about to do. So to do that, I'm going to, instead of using space claim, because it's a little bit slow to use if you don't use it every day, I'm going to go ahead and use SolidWorks. So now in SolidWorks, I'm going to create a new part by clicking this button here. I'm going to start out by creating a sketch. And I'm going to pay attention to my coordinate system here because in this instance, I'd like to keep it simple and keep my column vertical for buckling. So in order to extrude my cylinder along the z-axis, I'm going to click on the front plane. And now I'm going to get my circle tool to draw out my cross section. And it's just going to be a simple tube. I'm going to dimension my outer diameter as 25.4 and my wall thickness for 1 millimeter. The reason why I chose this dimension is it's reasonably standard for a tube on a bicycle, which is our project, for something like a seat post or the forks of the bicycle. A 1 millimeter wall thickness is something easy to remember and easy to calculate based on. And so this gives us a thin-walled tube in order to calculate buckling. I'm going to go ahead and extrude this. And we've calculated in a spreadsheet what length we would need to make sure that our failure mode in particular is buckling. And in order for that length to make sense, we need to be at 1.5 meters. The reason why we're choosing such a long tube is because if you have a tube that's shorter than that, then you don't necessarily know that it's going to be failing under compression from collapsing on itself or by buckling. For this example, we want to make sure that we're in the category of a very long column to make sure that we are demonstrating buckling. So now we have our tube. I'm going to go ahead and save this on my desktop so I can easily find it. Really long tube. I'm going to save it as a step file so I get that standardized output. And now I can go back to ANSYS, go to my geometry tab, right click on that, and you'll see an option for space claims so that I could have done it within ANSYS' software, or I could go ahead and import it as a step file. So I'm browsing my desktop, really long tube. My geometry is now a check mark, and you'll see that it linked that data across and it's now a check mark under eigenvalue buckling. But now I need to input model data for the mesh. And if I right click and hit edit, we're going to start mechanical. So now we're in mechanical, and you can see that we have our geometry, our coordinate system, and it's working in the z-axis as intended. We have our mesh, which has not been generated yet. You can see the little lightning bolt that says update or solve or generate. So there's something that we need to do there. We have our static structural module, which has a couple of settings on it. Our analysis settings has a number of steps that you want to iterate for, and it has many other controls that are beyond what we need to do. Under the Solutions tab, currently we don't have anything that it's solving for, so at the moment this module doesn't know what it's doing, and you notice it has a question mark here. If we go to the next module, Eigenvalue Buckling, we have another portion for setup. You'll notice that it says t is equal to 0. This is pre-stress. This is the data of our model before we've applied the forces in our static structural portion. So you'll see that the data is used in multiple places here. We have our analysis settings where we can find multiple modes covered in our theory section. For the sake of fun, we'll see what happens when we try and find 4 different modes. Although in theory, we will only see one mode in most applications when a force is slowly applied. In our solutions section, we need to add things that it'll be solving for. Currently, it's not solving for anything yet. In our geometry section, you can see when we click the plus that we have our model, really long tube. It shows our source of where our file is, as well as the type and the default units. Sometimes this can be a problem when your part imports and it's in millimeters as a default unit or in inches, and you can see what the unit is imported in here. If we go to our model,
We can also tell it what material it needs to be. It has defaulted to structural steel. But if you see in the drop-down, you can also select stainless steel. For the purpose of our project, we're going to switch it back to structural steel because we did our proofs based on structural steel so that we can make sure that we're getting the right answer. So the next thing on our list is coordinate systems. And you can see that it's already defined a global coordinate system and everything looks good, so we don't need to make any corrections here. Under mesh, we have a lot of options here. We have sizing. For our mesh sizing, we have many different options here. You can have meshes that are adaptive, that can change to the geometry of your part. You can also have meshes that react to certain curves, or if it's near other parts. Or you can just have a uniform mesh, so it's very simple. And in that case, you can choose your mesh size. I'm going to go ahead and generate this mesh so that we can see what it looks like. And here we can see our mesh in a uniform mesh. This is very reasonable for what we need to do, but let's go ahead and check out the other types so you guys can see what they're doing. Proximity, I don't think will do anything because we don't have any. Let's just choose adaptive and see what that does. So you'll notice in our model it looks the same as uniform because our geometry is extremely simple, that there's nothing special that's standing out. Even at the ends of our part, it's uniform and very basic. Now we need to apply our boundary conditions to our problem. I'm going to go ahead and click on static structural, right click and insert. And I want to first insert a fixed support. I need to apply a geometry. So I'm going to go up to my selection tools. On my selection tools, I have some options here. I want to select a face. You can select a single point, or an edge, or a face. So I'm going to select a face and click that bottom. I want to fix that bottom. And then click apply. So now this bottom is a fixed support. You can see that with the blue right here. Now we want to apply a compressed load. Zoom all the way out. I'm going to grab a box zoom tool and look at the other end. And that way I can apply my force on this end. So again, right click on static structural, insert. I'm going to add a force. Again, I need to select the other face and hit apply. And I want to define this force, instead of by using a vector, I want to use components because it's a little bit easier. Because I know I want my force in the positive z direction, as you can see from my coordinate system here. And I'm going to choose specifically only 1 Newton. The reason for this, within ANSYS, as it solves for the critical force required for buckling to start, it's going to solve that as essentially a safety factor. And if your safety factor is a ratio of the critical force to the force applied, if your force applied is 1 Newton, then the safety factor that you get is equal to the critical force applied to start buckling. So putting in 1 Newton just makes your math easier. Okay. So now I see force is 0. Let me make sure that's correct. 1 Newton there. In red, force 1 Newton. Okay, continuing on. in our solution. Let's add some things to static structural so we can see what it's doing. Let's insert deformation total, and that means when we run our analysis, we'll be able to see this color map of deformation that's based on our stress. And let's go down under eigenvalue buckling, and let's do the same thing. Insert deformation and total. And at this point, we may have everything, so let's go ahead and try and solve it, and let's see what we get, and if we have any problems, we'll work our way through it. Okay, it looks like we have an answer here. So I have my solution under eigenvalue buckling selected. If I zoom out, we can see the beam. I believe one of these buttons is to view all. There it is, zoom to fit. There we go. And we can see that we have more deformation towards the end that is not fixed up here. And if we look at our load multiplier, this is essentially our safety factor that we calculated from earlier. And so the force applied in order to create buckling within this beam is 1,253 newtons. And this gives us a lovely animation here. Now, last time I went through it, I only solved for 2 different modes. And this time, for fun, I went ahead and solved for 4 different modes. So if you look on the time graph here, it might skip between multiple methods of deformation. So it could be a little interesting. Let's go ahead and hit play. There's one mode, and it's just playing the one. This is just back and forth along a particular axis. I'm going to hit stop and see if I can select another one of these. This is probably the same. This just might be in a different axis. Now let's check our other mode and see if we get anything cool. It looks relatively the same, surprisingly. Oh, I can slightly see kind of a U shape there, but it's really, really faint. That's what I was expecting, a secondary peak. It's not as easy to see as I thought it would be. Alright, well, that was cool. That was basically all we're going to solve for. Now, within ANSYS, there's ways of exporting this information. You can go through solution information, and this prints out a document that you can submit to, say you need to submit it to your boss or customer for a project. This is your outputs here. And usually towards the bottom, there we go, there's our mode or our shape number, and then the load multiplier, and these are in newtons for our critical points for buckling. So this should summarize our ANSYS portion of buckling. As you can see, we had our fixed end support, applied our force at the end, and we determined for multiple different modes what that load multiplier needed to be, and that load multiplier, as explained, is the critical force required to start seeing buckling. And thank you very much. This has been the buckling team.